organizers for inviting me to this such nice conference. I'm very happy to be here again. Okay, so today I talk on such titles, and this is a joint work with my PhD student, Masura. Okay, so first I show some basic references. Today's talk is based on this one. It's just uploaded last week. Okay, and also we need this basic reference. It's collaboration with Kashiwara. And last year I taught this subject here. Okay. Here's preliminaries. This is basic notations. A means the symmetrizable generalized Cartan matrix, and then G is associated Kac-Moody algebras, and alpha I is simple roots, HI is a simple coroots, and lambda I are fundamental weights. They are satisfying these relations, and the Q is the root lattice, and the Q plus is the positive semi-subgroup. Okay, and then also we have some bilinear map, bilinear forms, and also P is a weight lattice, and the P plus is a dominant set of dominant weights. And the P star is just dual weight lattice, and the W, which is generated by simple reflection SI, is a wild group. And UQG is algebra, quantum algebra generated by these generators. And UQ minus is subalgebra of UQ, which is generated by only FIs. And the UQ plus is generated by EIs, and whose dual is usually called quantum coordinate algebras. Okay, later I'll show the definition of AQ and plus. And then crystal basis. So let A be the subring, sublocal ring, regular at Q equals 0. And the pair L and B is a crystal base of M. Here M is a module in integrable modules or UQ minus. If it satisfies the following conditions. First, L is a free A submodule of M, such that we extend the coefficient from A to Q of Q, then so we recover M from L. And the L also has a weight decomposition according to M. And the B is a basis of Q vector space L over QL. So you know L is free A submodule, then so this is well defined. Then so we have this, we can say this basis is Q equals 0, basis at Q equals 0. Okay. And also each vector is just a weight vector. And also L is stable by so-called Kashiwara operator A tilde and Fi tilde. So I do not define it so exactly, but sorry, so I omit. And also important property of B is this two property. First one is B. B is just a set because this is a basis. Okay, but still Ei tilde acts on B, so it means B Ei tilde or Fi tilde sends basis vector to other basis vector or 0. Okay, so this structure is very, very simple structures on basis. Okay, and also Ei tilde, Fi tilde are almost inverse. If it doesn't go to 0, it can go back. If it goes to Fi tilde and then Ei tilde, just inverse. If it goes to 0, it can't go back. It can't go back, okay? Then so Kashiwara shows that there exists a crystal basis for integral modules and the UQ minus. Okay. First of all, I define crystal graph. So by this property number 4, so crystal base B automatically has the graph structures by defining like this. So two vertices B1 and B2, so this connected by the arrow I is defined by this one, Fi tilde. So B2 is equals Fi tilde B1. then we have a graph structures on B. Okay. Later I'll show some example. Then so the definition, so here's V of lambda is a highest weight module, integrable irreducible highest module with highest weight vector U lambda. Then so L of lambda defined like this using Kashiwara operators. And the B of lambda also like this. Okay, and the B of infinity and the L of B infinity and B of infinity is defined similarly. Okay, then so Kashiwara shows that the pair L of lambda and B of lambda is a crystal base of B of lambda, or L of B infinity, B of infinity is just a crystal base of UQ minus. Okay. And the crystals. What is crystals? Crystal is just some combinatorial object, just abstracting the property of crystal bases. Okay. So just we take some set, and then so maps weight epsilon I phi I and the tilde fi tildes and the tilde fi tildes. So then they satisfy some conditions. So I omit it, but this property is coming from these properties. Okay. Because why we consider such things? So sometimes we need some combinatorial situation, but we don't need some module structures or algebra structures. Just some combinatorial situation we need. Then so we consider such things. The following example is just the important example of today's talk. Here take one index I from capital I, and set Bi is just a such set. But each vector is just parameterized by an integer. So as a set, Bi is just Z. Okay. The crystal structure is given as follows. Here weight is like this, n has an n alpha I. Alpha I is a simple root. And then the action vi tilde fi tilde is like this. So n to n minus 1, n plus 1, and n goes to n minus 1. Then the crystal structure, crystal graph is like this. Here 1 goes to 0 by I, 0 goes to minus 1 by I, and so on. So this is an infinite graph. This is a crystal graph of Bi. Okay. And also we can define the morphism between crystals. But this is a very usual, standard situation. Indeed, so map psi keeps weight or epsilon I, phi I, and also phi just commute with ei tilde, fi tilde, ei tildes. So then we call this map psi a morphism of crystals. And if morphism of crystals is injective, we call it embedding. And if it is bijective, we call it isomorphism. Okay. Then also important property of crystal bases or crystals, they have a tensor product structures. Okay. So if we have two crystals B1 and B2, then we consider that they are tensor product. Tensor product really, it's the set is just direct product of B1 times B2. Then their structure is, for example, weight is just a summation, or epsilon I, phi I. We need some max function. And the action with ei tilde, fi tilde, is very simple because it acts on left or right, only that. Then two conditions just separated by these conditions. Or fi tilde also like that. Then so we have the tensor product structures on crystal bases or crystals. Okay. Then so we consider the tensor product of these crystals right now. And also we have some isomorphism between them. Here we take Bi is just I defined in the example. For example, if I I and j satisfy this condition. So Aij is the entry of Cartan matrix. Aij equals 0, Aji equals 0. Then so Bi, Bj just commute. This gives the isomorphism. And if Aij, Aji equals minus 1, so this is simply raised case. This case we have three moves isomorphism. Bi, Bj, Bi is isomorphic to Bj, Bi, Bj. Okay? So the explicit form is given by this formula. And also this next is Aji equal 1, minus 1, and Aij equal minus 2. This is B2 or C2 case. Then so this is Ij is isomorphic to Ji, Ji. The explicit form is given by this one. And also opposite case, we have same under the same conditions. So Ji, Ji goes to Ij, Ij. This is isomorphism. Okay. And I omit. So we have also G2 case, psi ij 3, but today we don't need it, so I omit. Sorry. But you can find somewhere some just I show some references. Okay. Important feature is phi ij, phi ji are just inverse each other. Okay. So indeed, so this and this just inverse. And the phi ij1 is self-inverse. So you apply this twice, it goes back again the same identity. Also phi 0 also. Okay. So now we consider the cellular, so-called cellular crystals. Indeed, so by the braid type isomorphisms, then so if you take one value group element W and take the two reduced expressions of W, J1 and so on, I1 and so on, IL, and J1 and so on, IJL. Then so by this braid type isomorphisms, these two crystals are isomorphic to each other. So we call such crystals, we call this cellular crystals, because it's indeed it's obtained from the Schubert cell. By characterizing process, we have these crystals. Okay. So next is our second main subject, Quiver Hecke algebra. So to define it, we need some preparation. So first take some index I and field K and the family of polynomials Qij, two variable polynomial Qij, uv. It satisfies some conditions, good conditions, but I omit some parts, sorry. Indeed, so today we don't need it, but anyway, so there are some conditions. Okay, then so we can define the Quiver Hecke algebra R of beta. Beta is element of Q plus. Okay. The generator is three types. Here's E nu, xk, tau I. Okay, so three types generators. E nu is kind of projectors. Okay, and the xk is just commutative variables, and the tau I is just kind of Hecke generators. Okay, indeed their relations is like this. It's too much, so and it's complicated. But for example, here is the projections properties. Total summation of E nu is just a unit, okay? And also this property is just projections. Okay, and the xk is just a commutative, and so on. Then Q appears here and here. Polynomials Q appears here, okay? The important feature of this algebra is it has Z-graded structures. Indeed, if we set degree of E nu is 0. Degree of xk E nu is this. This is a bilinear form, so this is simple roots. And also tau L E nu is the degree of tau L nu. E nu is given this formula. Then so this algebra become Z-graded algebras. But here note that single xk or tau L are inhomogeneous. Okay, it's just mixed. If you apply the projection, so it becomes a homogeneous element, but the single xk or tau L inhomogeneous. Okay. Then so let's see something on our modules. First of all, we define the grading shift operator Q. Q is just applying Q. It means just we raise the grading 1. And also we also define the convolution product on 2 modules. So M is R of beta and N is R beta prime modules. Okay. Then so M circle N is just defined induced up functor like this. Then so this module is it's R beta plus beta prime modules. Okay. And then so M nabla N means head of M circle N. And M delta N means circle of M circle N. Here head of module is the quotient by its radical, and circle of modules is the sum of all simple modules, submodules. Okay. So in general, so circle and head is semi-simple modules, but in our situation, in many cases, circle and head become simple circle, simple head. Then so things become, how to say, good, become good. Okay, so R beta gmod means the category of finite-dimensional graded R beta modules, and then R beta g project, the category of finitely generated graded projected R beta modules. And note that so this category become a monoidal category by convolution product. Okay. Then categorification of UQ minus and AQN. Kumanov, Lauda, and Ruquier show that. Here K of RG mod with a Grothendieck ring of the monoidal category RG mod, and K RG project is a Grothendieck of monoidal category RG projects. And then they show that this algebra is isomorphic to this UQ minus, and then this one is isomorphic to AQN. So it is usually called categorification. Definition of AQN is this is the restrict dual of UQ plus. Okay. Here we define the functors EI and FI. Later, it's of course it goes to the generator of UQ minus, but the UQ categorification is just the generator is obtained by some functors. Okay. Here EI is the functor from here to here. Definition is like this. So M is a module. And also Fi is defined like this. It's just a convolution product with I and M. I is one-dimensional R alpha I modules. Okay, this is very simple modules, but it's very important. This role is very important. Also, we can define the EI star or Fi star. So, for example, Fi star is defined by M circle, so opposite side product. Then we can define the Fi star. And also, as we see, this has crystal basis. They have crystal basis B of infinity. So Lauda Bajrani consider that so also crystal base can be categorified, and then they succeeded in doing it. Indeed, the definition is like this. So weight is just take minus beta or epsilon I, phi like this, and EI tilde of M is circle of EI. EI is defined here. EI defined here. So take circle, then this circle just becomes simple circle. It means this is simple modules. Would plus some q power. This is a shift of degree. And also Fi tilde is defined by the following head of I and M. So here is the head, as I said, a head here. I defined it. Then so they show that this B RG mod be the set of self-dual simple modules in RG mode. And then the 6 tuple, this one, and the EI tilde here, Fi tilde, weight epsilon phi, holds a crystal structure. And there exists the following isomorphism from here to here. So this crystal is isomorphic to B of infinities. Okay. Next, let's see the definition of category CW. So W is a Wile group element. W is a Wile group element. And we define the WM like this. This is a subset of this part. And then so CW is defined as the monoidal full subcategory of RG mode by these conditions. Okay. When W is just the longest element case, then so this one just same as RG mode. Okay. So because this part just Q plus. So no, indeed this is no conditions. Okay, so next, so we define the determination modules because we need to define the localization of category. Determination module is defined by this formula. So here one is the unit, trivial modules, one-dimensional trivial modules. And each M1 and so M are defined by this formula. So here, sorry, I don't say this is the reduced expression of Wile W. And lambda is the dominant weight. Okay, then the module M W lambda lambda defined by this way. Okay. Then so we defined a general theory of braiders and real commuting families. So braider is some triple in monoidal category T. Okay. And it is graded by this Z lattice lambda. Okay. And also this product is denoted by tensor. Okay, a graded braider is a triple C, R, C, phi. C is an object in T, and phi is a linear map from lambda to Z. And RC is a C tensor X to Q power X tensor C, so it's just flip the product. It's like a R matrix, okay? Then using this, they satisfy these conditions, some commutative conditions, and then we consider that their family. So indeed, so this become a graded braiders, and then we consider the family, and also we need some conditions, commutativity conditions on these modules. But sorry, I omit it. But using this property, we can define the localizations of CW. And then we denote it CW tilde. Also, we can define the localization of RG mode. So we denote it RG mode tilde. Okay. So important features. So in general, CW is smaller than RG mode. But after localize it, CW tilde is category equivalence to RG mode tilde. So it means so many object just goes to 0 by localization process. Okay. So the localization in the process, so we use the following abbreviated expression. So M W lambda lambda is denoted by C lambda. Okay, so C lambda has such nice property, so product structures. then using this property, so we can define the localizations. So it's just like similar to the, in commutative ring theory, we just study localization of commutative rings. So this one just kind of analogous property like the multiplicative set in commutative ring theory. Okay. So the property of localization. Here QW is a localization factor from CW to CW tilde. Okay. Then so CW tilde is a abelian monoidal category. And QW factor QW is exact factor. And if we take the simple object S in CW, then so QWS is also simple in CW tilde. Then so this one, so CI is this one. Then it become the image CI tilde become invertible. What is invertible? So in category, object X is invertible if the factor X circle bar or bar circle X is just gives the category equivalences. We call it X is a invertible object. So this means so we can define the CI tilde inverse. Okay, then so for general lambda, weight lambda, not dominant, not necessarily dominant. So weight lambda can be written in the subtraction of two dominant weight mu and eta. Okay. Then so C lambda tilde is defined by this formula. C eta inverse circle C mu. And we need some Q power, so I forgot to write it here, but so we need it. And this definition does depend on the choice of mu and eta, okay? So this expression not unique, but this doesn't depend on the choice of mu and eta. Okay, and any object, simple object in this localized category is isomorphic to this object. C lambda tilde and QWS. QWS is from CW. Okay. This expression is not necessarily unique. For fraction 2/3 is same as 4/6. So this expression is not unique. So it's like, so this expression is not unique, but we have some expressions. Okay. Okay. And the crystal structures on CW tilde. Okay, but to do it, so we need some preparation. Sorry. First of all, rigidity. What is rigidity? So rigidity means any object has a left dual and right dual. What is right dual and left dual? So here, look this definition. So in category monoidal category T, object X and Y dual pair, or X is a left dual of X to X, or Y is right dual to X, if the following composition are identities. Here, epsilon is the morphism from X tensor Y to unit, and the morphism eta is unit from unit to Y tensor X. Okay. Then we consider that this and the 1 goes to here. Then X tensor Y goes to here. Then this composition, just the identity. Also Y is similar. This is identities. Then in that case, we say X and Y are dual pair. Okay. So CW tilde has a rigid. Always it has, every object has left dual and right dual. Because left dual and right dual are different. But every object has both. Okay. So it's wrong. So take C and grade the monoid category, and M and N be a simple object. If it satisfies the following conditions, so home M tensor N to N tensor M is one-dimensional. But note that, so this home is a little different from usual graded homomorphism, because graded modular homomorphism should be keep the grading. But this case, we just relax the condition. So I mean, we just arrow. So this map is goes to different degrees. Okay. But that is important because if it is one-dimensional, so we have a one generator Rmn. So we call it R matrix on M and N. Then so the degree. So as I said, so there exists some difference of degrees. So this difference of degree is denoted by this deg Rmn. So this is defined lambda mn. Then so we call it lambda definable of this one, m and n. Okay. So this value is very important to define the crystal structures on CW tilde. Okay. Now we defined. So L CW tilde be the set of equivalence class of simple objects in CW tilde up to grading shifts. Then the important data epsilon I, phi I, epsilon I star, phi I star is defined like this. Here lambda tilde is given by this formula. So lambda is just we define here, this one. And lambda tilde is defined like this. Here is the usual inner product on weights. Okay. And di is this value. And fi tilde defined qwi with x on nabla. This is the head of convolution product. And fi star tilde is just opposite. Flip this, then we can define. But ei tilde is defined using dual of qwi. And also ei star tilde, we need a left dual. This is right dual. This is left dual. So to define this one, so we need a property, this property. We need this one. Okay. Okay. Then finally, we have the how long I have?
Still have 10 minutes.
10? Okay. 10 minutes. Okay, so I am in a hurry. Okay, so the KWM is isomorphism from this crystal to BW. It is defined the following way. So ML is just M. And the CK is defined epsilon IK star of MK. And then so we can, from ML, ML minus 1, and so on, M1. Then we have the sequence of integers, C1 and so on, CL. So this gives us the image of these modules. Then then we can show that this is isomorphic to each other. Okay. Then so before doing it, we prepare this map E star W prime W. Okay. It's I don't say W prime. W prime is WSI. It's shorter than W. This order is just a Brillouin order. Okay. The important feature is KWX is this part is shorter W prime, and one component Fi tilde epsilon I star X 0I. So this one is our aim to obtain. Okay, so let's see the braid moves on cellular crystals. So there are 2 moves, 3 moves, and 4 moves. So it's simple. Ij, Ji, it's this case. Ij just flip. And the 3 moves is Ji, Aij equal 1. So Iji goes to Jij. And the 4 moves is Aij, Aj equal 2. So Ji is Jij, Ij. Also inverse. Okay, so in the circles, we use, we consider K is type A and B and C and D n, only classical types. And W is also the longest. Okay, we restrict our situation to this case. Okay. Okay. Then so we consider here the W0 under bar is the reduced expression of longest element W0. What we consider is any I. So we want to I just move to rightmost using moves, 2 moves, 3 moves, 4 moves, okay? Because we want to obtain the epsilon I star. Epsilon I star appears the rightmost, okay? Then so we want to using move, 2 moves, 3 moves, 4 moves, and then so each index I just goes to the rightmost, okay? Then finally we have epsilon I star x just on the right side, rightmost side. Okay. Then so type AN, BN, CN, DN case, we just consider some explicit way. For example, type A n case, we take the reduced longest word is like this. 1, 2, 1, and so on, n minus 1, and so 2, 1, and maybe this is kind of standard sequence. Reduce expressions of while group longest element. Okay. Then the element BW0 under bar is written like this. Okay. Each Zij is an integer. This or then just integers. Okay. Then so epsilon x is given by this using max function. So this is the expression form of epsilon I star x. Okay. This is the expression form. Type A. Type B, we take the following reduce the expression of longest element, 1 to n, 1 to n, and so on. This is cyclic one. Then so the epsilon for x, epsilon I x is given this really complicated formula. So epsilon I is defined like this, but zeta I is given this formula. And zeta I is given by using eta I. Eta I is given like this one, so it's really complicated formulas. But anyway, so we have very explicit formulas. Okay. And type Cn, the while group is same, so the reduced expression also same, and almost similar because but difference is only zeta I. So I only write here zeta I only here. But epsilon I and eta I is the same form. So this is type Cn. And type N is most complicated form. And then, so we take the longest word is like this, 1 to n, 1 to n, and so on. It's n minus 1 times. Okay, so x is in this form. And epsilon I star x is given like this. It's a completely complicated form. But anyway, so we have explicitly, okay, this is the formulas of epsilon I star x. Okay. Then, so what we'd like to do is the following theorem. If we take W0 is the longest element, and then this is some reduced expressions, okay? Then, so we consider the following conditions. So we consider the conditions, then they are equivalent. So weight x is 0 and epsilon is 0 for any I. Then x is given in this formula, 0, 0, 0, or 0. Of course, the inverse is trivial. From here to here is trivial, so we want this way. And then, so what it means. Okay, so we have the isomorphism KW. KW is where? Let me see, KW, here. KW, this is isomorphism of crystals. So it means, so 0, 0, 0 here, this comes from here by unit object is coming from here. Oh, no. Yeah. Then, so by this theorem, we have weight x in this irreducible modules, set of irreducible modules. No, it's irreducible simple modules. Okay. Then weight x equals 0 and epsilon equals 0. Then so x is just a unit up to grading shifts. Okay. So how to obtain this one? Of course, we use this explicit formula, type A, type D. Sorry, so I don't say this. This theorem is, of course, type AN, BN, CN, and DN. Okay, so sorry, I don't say it. Okay. Why we consider such things? Because before localization, before localized, so the category CW, W0 has crystal structures, irreducible objects has crystal structures. B of infinity is isomorphic to B of infinities. In this situation, so we only need to consider epsilon I star x equals 0. Then this gives us the x is the unit. We don't need weight is 0. But localized case, we have some counterexamples. For example, type A3 case, this object, of course, this is not 0, 0, 0, 1, 1, 0, 1, 1, 0. But this has every epsilon I is 0. So this is different from this one. So we need some other conditions. Then the condition is just weight is 0. We need this one in localized case. Before localization, so we don't need this way, this condition. Okay. Okay, sketch of a proof, but kind of how to say, kind of, yeah, okay. It's like just an example, okay. Anyway, how to move I to the rightmost. Let's see. These examples, A4 and I equals 3. So target index is 3. So we want to 3 will be on the rightmost. Okay. So the original reduced expression is like this. Okay, 1 to 1, 3 to 1, 4, 3 to 1. Okay. Then so we see I's occurrence of letter 1 from right. Okay, so this case, there's 4, 1 here, 4, 1 here, and the third one is 1, 2, 3, this blue one. Okay. Then so we see this blue one, and using these two moves, and then it goes to right as much as possible. Then it goes here, 1 to 1. So we have 1 to 1, always. Then so 1 to 1 goes to 2 and 2 by 3 moves. And next 2, we just go right as much as possible. Then so we have 2, 3, 2. So this case 2 goes to here, and we have 3, 3, 2, 3, 3. And the 2, 3, 3 goes to 3, 2, 3. Then so this case is end, because 1, 3 just commute. Then so 3 goes to the rightmost. But in general case, we need to continue. So and then finally, but we have this sequence I minus 1, I. And finally, so I just gives us the epsilon I star. Okay. So this is type A. And the type B, type C, and type D, it become more and more complicated. So I omit how to do it, but we have. Okay. Then, so applying braid type isomorphism on the vectors, then we have the explicit form of epsilon star 3 star using braid type isomorphism between crystal bases, crystals. Okay, then so the following is just we consider the conditions epsilon 1 equals 0, epsilon 1, epsilon 2 is 0, epsilon 3 is 0, epsilon 4 is 0, and also weight 0. Then we have the following conditions. Then finally, we have these conditions. All Zij is 0. And indeed, so we have already E6, maybe yes. E7, G2, yes. G4. But E8 is a little complicated. It's very long and it's so complicated. So we just stuck now, but we need to solve it. But anyway, so we are trying to this exceptional cases. Okay, merci beaucoup.
Questions? Okay.
So, when you compute this dual Kashiwara operators, it's on like start. So then in usual case without categorification we can do this using this energy decoration function or gross heightened field conservative potential. And so is any idea how to categorify potential?
Yeah, it's interesting problems, but so function, I'm not sure how to categorify functions. So
yes, okay. Object, we have morphisms. So what would be?
Yeah, but yes, yeah, yeah. So how to say? It's not easy question. So, but yeah, sorry, I don't know right now, but yeah, I think it's interesting. Yeah.
That was just a historical question. So then you just write this braid relation. So it was first a new paper.
Yeah. Yeah. Sorry. Okay. This one. Second.
99.
Yeah.
Maybe the same time than Bernstein and Zelinsky because it's string.
Yeah. But they know it too. Yeah. I discussed with them. Yeah. Okay.
Thank you. Thank the speaker.
Thank you.